Well, hello everybody. Today we're going to continue on with section 15.2 that deals with limits and continuity. And the first thing that we're going to do is we're going to look at the somewhat formal definition of a limit. I don't want you there frantically copying it down because we're not going to be using the formal definition to evaluate our limits, but let's just read it right here first. It says, let f be a function of two variables whose domain D includes points arbitrarily close to some particular point AB. Then we say that the limit as xy approaches AB of f of xy equals L. If given any epsilon greater than 0, there is a corresponding number delta such that whenever you have a point xy that's in the domain and at the same time xy is within delta of AB, then it follows that f of xy will be within epsilon of L. Instead of frantically copying that down, I want to sort of look at it pictorially, what's going on here. So the first thing that's going on here is we have some limit, L, all right? We want to say that the limit as xy approaches AB of f of xy equals L. Limits act just like they did when you took Calculus 1. The whole idea is as xy gets closer and closer to the point AB, what is f of xy approaching? And so this should be an L here, by the way. We're saying that if we claim that the limit as xy approaches AB of f of xy equals L, it says if you give me some small number epsilon, and I look at some interval around this number L, epsilon less than L, epsilon more than L. So the endpoints of this interval are L minus epsilon to L plus epsilon. And we're saying that if you give me this epsilon, if you give me some epsilon greater than 0, then I can find some disk around the point AB. All right, so that and this disk is of radius delta. If I look at all the points in that disk, inside the interior of that circle, if I take any point xy that's within delta of AB, and definitely the distance from here to here is going to be less than the radius of that circle delta. If xy is in that disk, xy not equal to AB, then f of xy is going to have to be within that interval. And so the whole idea is as xy gets closer and closer and closer to AB, what does f of xy approach? And just like in Calc 1, you weren't allowed just to plug in because it wasn't what's happening at AB, it's what's happening as I get close to AB. All right, and we're going to talk about how to evaluate this limit when you have 2 variables, 3 variables, 4 variables. What do you do? All right, first of all, I want you to notice something though. Since we're saying as our xy's get closer and closer to AB, notice when you took Calc 1, x got closer and closer to your A as you came in from the left and you came in from the right. Notice AB, there's multiple ways I can approach AB. I can approach from above, I can approach from the right, I can approach from below, I can approach from the left. I could approach in some curve that does this. There's infinitely many different pathways I could take in 2-dimensional space in which I get closer and closer to AB. So notice, if I'm looking at the limit as xy approaches AB of some f of xy, all right? And maybe this is my y-axis, this is my x-axis, and maybe AB is here. Since we're saying xy is getting closer and closer to AB, notice maybe you take one path coming this way, and we'll call that curve 1, and maybe you're coming towards AB in another path, curve 2. If I look as I'm coming along curve 1 and I look at what my f of xy's are going as I go along C1, and if I look at what are my f of xy's going to as I go along some curve C2, if you're getting 2 different limits there, then there's no way the limit can exist. Just like in 2-dimensional space, you came in from the left, you came in from the right, and we said if those 2 limits were not equal to each other, then your limit did not exist. The problem here is, in Calc 1, you had 2 different pathways that you could take. In Calculus 3, there's infinitely many pathways that you could take. So the point is how? How do I go about evaluating this limit? All right, well, first of all, I wanted to note here, if you have as f of xy approaches L1 as xy goes to AB along some path C1, and f of xy is approaching L2 as xy approaches AB along some path C2, then we do say the limit does not exist. So if you can find 2 different pathways, 2 different ways to go to AB, and the limits of those 2 pathways are different, God is good and there's no limit. Okay? So I'm listed here 4 different ways in today's lecture that we're going to determine our limit. Just as we did in Calculus 1, algebraically, factoring, playing plug-in with polynomials or rational expressions, we're going to do just like we did in Calculus 1. Method 2 is find 2 paths to the point that will render 2 different limits, and if your 2 different paths render 2 different limits, then the limit does not exist. We'll also find, even though I'm sure some of you say, no, but yeah, polar coordinates sometimes are very, very helpful when your xy is going to 0, and we'll talk about those in a few minutes. Okay, and fourthly, we use this a little bit in Calc 1 and a little bit in Calculus 2. The squeeze theorem sometimes is helpful, and we'll have an example of that. All right, so these are 4 ways that we can figure out our limit as xy is approaching some AB in 2-dimensional space. Okay, so first of all, the first one I want to look at is the limit as xy goes to 0, 0 of x to the 4th minus y to the 4th over x squared plus y squared. All right, and if you notice, I did put on if you do the printout, I have little hints down in the right-hand corner, and what you might want to very well do is after today's lecture, you might want to go back over these examples, and see how would I evaluate this limit? What's one way I can do that one? And I will mention also that sometimes you can evaluate a limit using any number of the different methods that I listed. You could factor, you could do it algebraically, you could use the squeeze theorem, you could use polar coordinates, and multiple methods would work. But this one's a very easy one. We're taking the limit as the point xy gets closer and closer to the origin 0, 0. This one cries out to me, notice the numerator I can factor. Okay, so what we're going to do is we're going to factor our numerator. And so if I factor it, I get x squared minus y squared times x squared plus y squared all over x squared plus y squared. And remembering xy is approaching 0, 0, but it's never allowed to equal 0, 0. And therefore, what I have right here, as xy gets closer and closer to 0, 0, but never able to equal it, this is a form of 1. It will never be 0, 0 because xy gets close to 0, 0, but does not equal 0, 0. And so this is a form of 1. And so therefore, this is equal to the limit as xy approaches 0, 0 of the expression just x squared minus y squared. And just as in Calculus 1, when you have a simple polynomial and you take a limit, plug it in, because polynomials are beautifully continuous. So I get 0 squared minus 0 squared, which is 1 big fat 0. So if you can factor and reduce it, definitely. And just like in Calc 1, if you had played plug-in, you got 0 over 0, that means I have to do some algebra. Let's see if I can factor. Okay? Unfortunately, in your homework tonight, very little of it factors. Okay? We'll see other methods that we have to use. All right, looking at this one, again, this is a polynomial just like in Calculus 1. When you have a polynomial, what you can do is plug in. And so the limit of this will equal, I'm plugging 1 in for x and 2 in for y, so I'll get 1 squared times 2 cubed is 8, minus 1 cubed, which is 1, times 2 squared, which is 4, plus 3 times 1, which is 3, plus 2 times 2, which is 4, which gives me 8 minus 4 plus 3 plus 4. Quite nicely, the 4's cancel. And it looks like our final answer is 8 plus 3, which is 11. So when you have a simple polynomial, plug in. Okay, not hard. All right, here's another one. Now this one I'm just sort of nudging us along. It says, show that the limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared does not exist. All right, now in your homework tonight, I would always be under the assumption that maybe perhaps the limit does not exist. Unless you have a simple polynomial or you have a rational function where you can just play plug in. Now notice this rational function, if I play plug in, I get 0 minus 0, which is 0 on the top, and 0 plus 0, which is 0 on the bottom, and 0 over 0 is indeterminate. Okay, so I don't know yet if the limit exists or not. Now notice, here's the y-axis, here's the x-axis, here's the point 0, 0. And we want to get closer and closer and closer to that point without touching it. There are multiple paths to take. In Calculus 3, when we're first evaluating these limits, the first path I'm going to take is going to be coming along the x-axis. Now, how can I name a general point on the x-axis? On the x-axis, I think all of you would agree that the y-coordinate is 0. Okay? So, if I'm just coming along that path, I'm going to be taking the limit as x0 approaches 0, 0. Okay, you all with me? Because I'm just coming along the x-axis. So I'm going to plug in x in for x, but I'm plugging in 0 in for y. X in for x, 0 in for y, and I get the limit as x0 is approaching 0, 0 of x squared over x squared, which is equal to 1. So coming in this way, I'm getting a limit of 1. Okay? Now, if I do 25 other pathways and I always get 1, that does not tell me the limit exists. That tells me probably the limit exists, all right? But there might be a 16th pathway that gives me a different value. But if I can find 2 pathways that have 2 different values for their limit, then the limit does not exist, all right? So the first pathway I took was going along the x-axis. My second pathway, I'm going to try going along the y-axis. Now, if I'm coming in along the y-axis, what's an arbitrary point on the y-axis? X is 0 and y is y as I come down along the y-axis. So a point on the y-axis is 0, y as we go from 0, as we approach 0, 0. And again, our expression is x squared minus y squared over x squared plus y squared, but we're putting a 0 in for x and a y in for y. And I get the limit, and really 0 is always 0, but y is approaching 0, of minus y squared over y squared, which gives me a -1. So coming in from the x-axis, positive x-axis, I got a limit of 1. Coming in from the positive y-axis, I got a limit of -1. Since I have 2 pathways with different limits, we say that the limit as x comma y approaches 0, 0 of x squared minus y squared over x squared plus y squared does not exist. Okay, so usually my method of attack when I'm doing these is maybe I can find 2 pathways that will give me 2 different limits. Okay, all right, let's do another one. If f of xy equals xy over x squared plus y squared, does the limit as xy approaches 0, 0. And you'll notice in your homework, almost all the time he has xy going to 0, 0. I don't know why he always did that, but he's done that a lot. Does it exist? So what we're going to do is we're going to say, okay, let's go along the x-axis first. Is that going to work? Coming along the x-axis, a point on the x-axis is x comma 0. And as you let x approach 0, you're going to be getting closer and closer to the point 0, 0. So we're taking the limit as x0 approaches 0, 0. And so what we're plugging in here, for x, I'm plugging in x. For y, I'm plugging in 0. For x, I'm plugging in x. For y, I'm plugging in 0. And I get equals the limit as x0 approaches 0, 0 of x times 0 is 0. X squared plus 0 is x squared. And as x0 approaches 0, 0, the numerator is always 0. The bottom is 1 squared, or 0.5 squared, or 0.3 squared. Who cares? X cannot be equal to 0. 0 over anything, as long as it's not equal to 0, is 0. So my limit coming in from the left is 0. Okay? What do you think we're going to do next? I think we're going to take the limit from the top, from the y-axis, huh? Let's try that one. Okay, so I'll just put this one aside. So coming along from the x-axis, I got 0. I'm thinking, let's do it along the y-axis, just like we did in the first example, right? Well, a point on the y-axis is x is 0, y is y. So we're taking the limit as 0y approaches 0, 0. And we're coming down this way. And again, we're plugging 0 in for x, y in for y, 0 in for x, y in for y. And I get the limit as 0y approaches 0, 0 of 0 times y is always 0. 0 squared plus y squared is y squared. 0 divided by any non-zero number is 0. Now at this point, don't tell me, oh, Mrs. Strocko, I took 2 paths, I got 0 on both of them, and therefore the limit is 0. you took two paths, you got a limit of 0, but how many pathways are there? Infinitely many. You might have just been lucky or unlucky that you have two paths with the same limit. This does not prove to me that the limit is 0. It might support that it might be 0, but we don't know that it's 0 at this point. Okay, so how else could we do it? Well, let's try another pathway. Why don't I come along the line y equals x? I could come along the line y equals x and come down this way. That's another pathway, isn't it? Now, why did I look at it that way? Well, I'm thinking, you could, how would I name an arbitrary point on the line y equals x? Well, normally the point would be x comma y, but since y equals x, we could call it x comma x. Do you see, as x goes to 0, x is going through the origin, 0, 0. All right, and therefore, this would be the limit as x approaches 0, 0 of, I'm putting an x in for x, an x in for y, an x in for y, and what do I get here? I get limit as x approaches 0, 0 of x squared over 2x squared, which is always equal to 1/2. You see, coming in along the x-axis, I got 0. Coming in on the y-axis, I got 0. Coming in obliquely, I got 1/2. I have two different pathways with two different limits, and therefore this limit does not exist. So just because you got two pathways getting the same limit, your work is not done. Okay? It might take a third or a fourth try. The most important thing is the pathway you pick must, notice, as x approaches 0, the point x definitely is going to the point 0, 0. You have to make sure the pathway that you've represented is going through that point, 0, 0. Okay, so let's look at another one. Let's look at this one. This one, you're going, oh my goodness, I've got trigonometry to deal with, all right, but that's not too bad. I always try going along the x-axis and along the y-axis first. So if we come along the x-axis, to determine a point on the x-axis, how do we represent it? We represent it as x, 0, right? And we're letting x go to 0 because we're going to the origin. Because notice this one again is going to 0, 0. So we have the limit as x, 0 goes to 0, 0. And so in our function, we're plugging x in for x, but 0 in for y, x in for x, but 0 in for y. And this gives me the limit as x, 0 approaches 0, 0 of, what's the sign of 0? 0. So it's x squared over 2x squared, which is 1/2. So coming in along the x-axis, I have a limit of 1/2. Let's try coming in along the y-axis. All right? If I'm going to come in along the y-axis, a point on the y-axis, let's write it as 0y. Coming in along that way, we're letting 0y with y going to 0. So this is equal to the limit as we're going 0y goes to 0. I shouldn't even say equals, because this is every single pathway that you could imagine. You have to get the same answer. But let's see. I'm putting a 0 in for x, a y in for y, a 0 in for x, a y in for y, and I get the limit as 0y approaches 0, 0 of sine squared y over y squared. Does anybody remember from Calc 1 or Calc 2 what the limit is as y goes to 0 of sine y over y? It's 1. If you don't remember, if you plug in here, you get 0 over 0. You with me? I got 0 over 0. If you have 0 over 0, you can use L'Hopital's rule. This would equal the limit as y approaches 0 of the derivative of the top over the derivative of the bottom. Derivative of sine is cosine. Derivative of y is 1. And when you plug in here, you get 1 over 1, which is 1. So sine y over y as y goes to 0, it's a classic. That's equal to 1. So with this one is the limit as 0y goes to 0, 0 of sine y over y squared. So what's in the parentheses is going to 1, so it's going to 1 squared, which is 1. So wait a minute. Coming in from this way we got a half, and coming in this way we got a 1. So what can you tell me about the limit? It does not exist. So I usually go along the x-axis and along the y-axis. If I get different limits, I'm done. If I get identical limits, my work is not done. How about this one right here? This one has 6x cubed y over 2x to the 4th plus y cubed. All right, now let's just first try the path along x0. And we're going to get the limit as x0 approaches 0, 0. And if I plug in an x in for x, a 0 in for y, because see, this is your x, y, so you're putting 0 in for y, an x in for x, a 0 in for y, I get the limit as x0 approaches 0, 0 of 0 over 2x to the 4th. 0 divided by anything that's not equal to 0 is 0. Now, I don't want to bore you to tears too much, so take my word for it. If I came down this way, you'd get 0 again. We're not going to do it just to save ourselves time. If the limit from the left is 0 and the limit from coming above is 0, does that tell me that the limit is 0? No. It just means you haven't proved yet that the limit exists or it doesn't exist. You've just taken 2 pathways out of the infinite number of pathways. So we're going to save time and not come in from the top, because I already did it before and I saw that I got 0. So I look at this and I say, I need to have a different pathway. Now this is where, with the problems in your homework tonight, you have to be a little bit clever. Wouldn't it be lovely if for here, for y, I'm looking here, this is 2x to the 4th. Notice, if you let y be x, you'd have 6x cubed times x, 2x to the 4th plus x to the 4th. Everything would be in terms of x to the 4th. Now, does the path y equal x go through the origin? Well, sure it does. The path y equals x looks like this, right? Do you see why I picked it, though? Because I'm thinking if I had x cubed times x, I'd get x to the 4th. Everything would be in terms of x to the 4th. So we're going to take the pathway x comma x. We all see that? Because I'm letting x be x, but since y is equal to x, I replace y with x. So now I'm taking the limit as x goes to 0, 0. And when I plug that in, I have 6x cubed, because x is x, but we're letting y be x. So I have times x over 2x to the 4th. We're letting y be x. And I look at that, and what do I get here? I have the limit as x approaches 0, 0 of 6x to the 4th over 3x to the 4th. What's that limit? 2. Because the x to the 4ths cancel, don't they? The x to the 4ths cancel. 6 over 3 is always 2. So, coming in from the right, coming in from above, we got a limit of 0. But coming in obliquely along the y equals x, we got a limit of 2. We have 2 different pathways, 2 different limits. Does not exist. And by the way, when you take your test at the end of this chapter and you're asked to either show that the limit exists, determine the limit, or show that it does not exist, you have to show me the pathways. You just don't put a big D and E there. You with me? You have to show me, 2 different pathways that you would get. Here's another one. In this one, take my word for it. Let's go along the x-axis. We're going to let x0 go to 0, 0. And if I do that, notice if x is x, but y is 0, you're going to get x times 0, which is 0 over x squared. And as x is approaching 0, 0 divided by anything, as long as it's not. Because you see, x is not allowed to equal 0. It just gets close. 0 divided by 0.01 cubed is still going to be 0. Now notice, if you took the limit and you wanted to come in this way, that would be the point 0y going to 0, 0. Notice, since you're putting a 0 in for x, you're getting 0 in the numerator, y to the 8th. You get a 0 again. So I go, oh, coming in this way, I got a 0. Coming in that way, I get a 0. And then I think, oh, I've got to have some better way. I've got to find out some other. Now, if you let x equals y, it's not going to be that easy to figure out. All right, so instead, let's look at this. This is where Mrs. Strocko is like, how can I hedge my thing? Notice here I have y to the 8th. Wouldn't it be nice if the numerator was y to the 8th? Now, how would I make the numerator be y to the 8th if I got a y to the 8th here? I'd have to let y be, or I'd have to let x be y to the 4th. Does anybody know what the graph x equals y to the 4th looks like? It looks like a parabola on its side. It looks like that. Does it go through 0, 0? Well, yes, it does, because when y is 0, x is 0, right? So I'm going to take, and how would I represent this point right here? I'm going to let y be y, and I'm going to let x be y to the 4th. Do you all see how I did that? I let x, since I would love to make x be y to the 4th, I know this looks like that, so definitely it goes to the origin. I can see 0, 0 satisfies it. So we're letting x be y to the 4th, so y is y, and x is y to the 4th. So we're taking the limit as y to the 4th y approaches 0, 0. And we're putting y to the 4th in for x, y in for y to the 4th in for x, y in for y. And what does this give me? This gives me the limit as y to the 4th y approaches 0, 0 of y to the 4th times y to the 4th is y to the 8th. Y to the 8th plus y to the 8th is 2y to the 8th. What does that limit equal? 1/2. So coming in this way or coming in this way, we got a limit of 0. But coming in this way, we got a limit of 1/2. And therefore, what can you tell me about the limit? Does not exist. Okay? I think we did enough of those. So let's go on and let me show you another way that you can do the limit. In Calculus 2, most of you had polar coordinates. And polar coordinates were very, very helpful. Notice, if you have a point in two-dimensional space, you can write your coordinates as x comma y, but you also could write them as r comma theta. We reviewed these a bit in the chapter 13 when we did the cylindrical coordinates. Okay. Now notice, what was r? What was r? It was the distance the point was to the origin, right? Well, if xy is approaching 0, 0, if xy is getting closer and closer to the origin, what is r approaching? What's your distance that the point is from the origin going to be? It's going to be approaching 0. So many times, if I need to do a limit and I have the point going to the origin, sometimes life is very, very easy if you change it to polars and just let r go to 0 and see what you get. Believe it or not, in this instance, many times, polars make life easier. Now, I'm a little upset with your book because they just put the polars like in the very last problem. You know, it's like number 37, they say, oh, use polar coordinates to do the following. In our class, many of the and I know many of you are very dutiful when you're doing your homework and you have your student solutions manual opened up and you're like, I have to do it like they do it. No, 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 no. You don't have to do it like they do it. All right? You can use polars sometimes, and you're going to see this. They're going to be doing it with the squeeze theorem and all this fancy stuff. And you can do it with polars like in 2 lines and you'll be done. Now the only thing to remember, if we do polars, we have to transpose it into r's and thetas instead of x's and y's. Does anybody remember the relationship between x, y, r, and theta? Remember, r is how far the point is from the origin. Theta is your angle in standard position. Since this is the adjacent side right here, notice x equals r cosine theta. And this is the opposite side, so y is equal to r sine theta. So if you're changing it to polars, remember, x equals r cosine theta, y equals r sine theta, and having x, y approach the point 0, 0 is the same as letting r approach 0. And now your book says r from the positive side. Well, yeah, because the distance that a point is from the origin is going to be positive. Okay? So this one, we could take multiple paths, all right, with this one right here. The limit is xy goes to 0, 0 of x cubed plus y cubed over x squared plus y squared. And I invite you guys at home, you might want to just stop the tape right now, and you might want to try the path x0 as x goes to 0 and 0y as y goes to 0. You can try x comma x squared, x comma x to the third. You can try 25 different paths. Every time you're going to get 0. So you're going to go, wow, but Mrs. Strocko said if you have 100 paths that it's going to 0, that doesn't necessarily tell you that the limit is 0. You just weren't clever enough to find one that has a different answer, right? With polars, if you think the limit is 0, you can prove that the limit is 0 and be done with it. So watch what we're going to do here. Oh, by the way, with polars, and I mean with polar coordinates, what's the relationship between x, y, and r? Remember, it makes a right triangle, right? Pythagorean theorem. It's very important to realize that x squared plus y squared equals r squared. It's a very nice identity to remember with polar coordinates. So this one, you could have spent, you know, the next hour, if you turn my tape off, and every single path you took, it looked like the limit 0. But having 25 paths is not enough. So we're going to change it to polars. So we're going to let x be r cosine theta. Notice if xy is going to 0, that means r is going to 0 from the positive side. So if x is r cosine theta, and y is r sine theta, and we all know x squared plus y squared is r squared, let's evaluate this limit a little bit. This equals the limit as r goes to 0 from the positive side of r cubed cosine cubed theta plus r cubed sine cubed theta over r squared. I think most of you would see you could factor out an r cubed on the numerator. And what can we do with the r's? We can cancel them. And we have the limit as r goes to 0 from the positive side of r times cosine cubed theta plus sine cubed theta. Now, I don't know what theta is. I don't know what theta is. But this is going to be some number between, well, cosine cubed is going to be between -1 and 1. Sine cubed is going to be between -1 and 1, right? This is going to be some number if you add them between -2 and 2. But what's r going to? So this is some number between -2 and 2. And this is going to 0. Well, this is going to 0. 0 times something that's fixed between -2 and 2 is going to give us 0. And so my limit is 0. So with polars, we don't have to do 25 paths. So my point is this: if you do like 2 or 3 paths and you're getting 0, 0, 0 all the time, I'd say let's give the old polars a try. Okay? Without further ado, let's do another one. This one, xy squared over x squared plus y squared. Take my word, you can take different paths, and the many different paths that you try, you're getting 0. So you're thinking, I can't seem to be able to prove that the limit does not exist. Let's see if I can use polars to show that the limit is indeed 0. All right? So we're going to again let x equal r cosine theta and y equal r sine theta. So we're taking the limit. Now notice xy is going to 0, 0. So r is going to 0. So I have for x, I put in r cosine theta. For y squared, I put in r squared sine squared theta. And for x squared plus y squared, I can put in r squared. So this gives me the limit as r approaches 0 from the positive side of r cubed cosine theta sine squared theta over r squared. A pair of r squareds cancel. And I get r cosine theta sine squared theta. This is some fixed number, depending on what theta is. R is going to 0, so what's this thing going to? 0. We're done. We're done. So polars are really great when you have a limit of, when it looks like your limit's 0. Notice, a key to me is when the denominator is x squared plus y squared, that's an easy r squared right off the top of the bat. Let's try polars. Okay, now if you notice, you look, I put little things on the bottom here. I have written polars help or squeeze theorem. So let's talk about how would we do this with the squeeze theorem, even though I think most of you are going to agree that you like the polars better. Remember, the squeeze theorem was this. If you had functions f, g, and g sandwiched between f and h, what the squeeze theorem said is the limit as you're approaching something of f is going to be, let's say less than or equal to, is less than or equal to the limit of g, which is equal to the limit of h. Okay, that makes sense, right? If this is less than that. Now, Granted, I'm assuming that all of these have x, y going to the same point, a, b, all right? Well then, suppose this limit was L, and suppose this limit was L. Well then, the limit as x, y approaches a, b of g would also have to be L, because the limit's sandwiched between L and L. And that was called the squeeze theorem. Your book in the Student Solutions Manual loves the squeeze theorem for a number of your problems. If you don't like the squeeze theorem and the limit looks like it's going to be 0, try polars. They're a little bit easier to do. All right, but in this particular one, let me show you how they did it. You plugged in a few, and it looks like this sucker's going to 0. All right, so I think all of you would agree that x squared plus y squared is always going to be greater than or equal to x squared. Do we all agree that? Yeah? So 1 over x squared plus y squared is less than or equal to 1 over x squared. If this number is bigger than that number and they're positive, then the reciprocal of this is less than or equal to the reciprocal of that. All right? So if I multiply through by, let's assume that x and y are positive right now. I'm going to assume x and y are positive. If I multiply through by xy squared on both sides, okay, or if we don't want to assume that xy squared is positive, let's just make it be absolute value. Okay? Well, then I think you'll notice this 0 is less than or equal to this, because this is a positive over a positive. And this one, oh, I didn't want x squared on the bottom. What do I want? I'd love to have y squared on the bottom so that they would cancel. So let's go back up here. Would we all agree that x squared plus y squared is bigger than or equal to y squared? We all okay with that? So 1 over x squared plus y squared is less than or equal to 1 over y squared. So if I multiply through by that, I'll have a y squared here. Now the y squareds cancel. Okay? Now, if we let x, y go to 0, 0, 0 is going to 0. What's this baby cake going to? What's absolute? It's going to 0. So since this guy is sandwiched between those, what's he going to? 0. Well, if the absolute value of something's going to 0, your thing's got to be going to 0 too. So therefore, the limit as x, y approaches 0, 0 of, I'll just say ditto of what we had above, is 0. Now, I think polar coordinates are a little bit easier. Okay, but you're more than welcome to use the squeeze theorem. And if you're one of those that dutiful always thinks that, Student Solutions Manual is God, I have to do what it says, you're welcome to do the squeeze theorem. This one, let me tell you, if you plug in a few of these, you can try x0, you can try 0y, you can try xx, you can try x comma x squared, you're going to get 0. So you think, I think the limit of this looks like he's 0. But 25 paths giving me 0 does not prove that the limit is 0. Let's try polars. So with polars, I'm going to let x equal r cosine theta, y equal r sine theta, and remember that x squared plus y squared is r squared. So playing plug in here, this is equal to the limit as r goes to 0 of 3 times r squared cosine squared theta, because it's x squared. For y, I'm putting in r sine theta. And for x squared plus y squared, I put in r squared. So this gives me limit as r approaches 0 from the positive side of 3r cubed cosine squared theta sine theta over r squared, which gives me the limit as r approaches 0 from the positive side of 3r cosine squared theta sine theta. No matter what theta is, the biggest that can be is 1 times 1, right? The least it can be is -1. But r is going to 0. So what's this limit going to? 0. We are done. Polars are wonderful. Okay? Okay, let's do another one. This one, God is not as good. And the reason is the denominator is x squared plus 2y squared. It's going to be a little bit bloody. Okay? You can try the path x0, you're going to get 0. You can try the path 0y, you're going to get 0. You can try the path xx. So you go, how can I prove this? This one, unfortunately, the only way I know how to prove it is with the squeeze theorem. All right, so it looks like the limit's 0, but with polars, it's not going to be as nice. Notice, I would love to have the x squareds cancel here. So I'm going to say, wouldn't it be lovely to get rid of that stinking 2y squared? Well, do we all agree that x squared plus 2y squared is greater than or equal to x squared? This is bigger than that. Okay, we all okay with that? So the reciprocal of this is less than or equal to the reciprocal of that. So I have this bottom is less than or equal to that bottom. Now what I need is that for my numerator. Do all of you realize that that numerator is always positive? X squared sine squared y is always positive. So if I multiply through by the numerator on both sides, since it's always positive, don't have to worry about changing my inequality. So on the left-hand side, I have x squared sine squared y over x squared plus y squared is less than or equal to, on this side, the x squareds cancel, and I just get sine squared y. Now this is a positive, positive over positive, so this is always bigger than or equal to 0 because it's positive. So this is less than or equal to this, which is less than or equal to this. I've squeezed this guy in between these two. So as xy goes to 0, 0, this guy is going to 0, right? This guy's going to 0, because 0 is always 0 is 0 is 0. But what's sine y going to? As y goes to 0. What's the sign of 0? 0. So the limit of this is 0. The limit of this is 0. Since he's sandwiched between those two, his limit must be 0. I'll have to do some soul searching whether I want to put squeeze theorem on your test. Because it definitely is an art form. It takes a fantastic amount of mathematical maturity to go like, how do you know what to pull out? Okay? So it's not easy. It's not easy. Polar coordinates is a piece of cake. Different paths is a piece of cake. Factoring is a piece of cake. Playing plug-in if it's a polynomial, piece of cake. Okay? All right. We have a couple more things we need to talk about. Back in Calc 1, those of you that had me, I know, and no matter who you had for Calc 1, I'm sure you talked about continuous functions. So let's just go over the definition. A function f of two variables is called continuous at ab if the limit as xy approaches ab of f of xy equals f of ab. If you had me, you remember I used to say, you're continuous at ab if the limit is equal to what you get when you play plug-in. Okay? We say f is continuous on its entire domain if f is continuous at every point ab in the domain. Remember back in Calc 1, we had various functions. You had polynomials, you had rationals, you had the trigonometric, you had the logarithmic, and you had the exponential. If you might remember, we proved that all of these functions were continuous on their domains. So as long as they were defined, these particular functions, to evaluate the limit, all you had to do was play plug-in. In two-dimensional space, guess what? Same rules hold. If it's a polynomial, play plug-in. If it's a rational, if you can play plug-in, plug-in. But if you have 0 in your denominator, you might have to do some work. Okay? Trigonometric, the same thing. If you can play plug-in, go ahead. But if you get 0 over 0, time to do some work. Same thing with logarithmic and exponential. Okay, so let's evaluate some. A rational function is continuous on its domain. So are the polynomials, the trigonometric, and the logarithmic, and the exponential. So the question is, where is this function f of xy, which equals x squared minus y squared over x squared plus y squared, continuous? As we said a few minutes ago, or 10 seconds ago, a rational function is continuous on its domain. So I look at this function, I say that's a rational function. A rational function is a ratio of two polynomials, right? This function is continuous on its domain. So all you have to do is come up with what is its domain. With rational, what's your only no-no? You can't have 0 where? In the denominator. So we can't have x squared plus y squared equal to 0. How can you have x squared plus y squared equal to 0? How can that happen?
0, 0.
The only way that can happen is for xy to be the identical point 0, 0. That's right. So your domain is all reals except the point 0, 0. You could write it as the set of all x, y, such that x does not equal 0 and y does not equal 0. That's fine also. So the domain for that particular function is all reals except has a little hole right at the origin. Okay? How about this one? Now, this one is a piecewise function. I'm defining it to be x squared minus y squared over x squared plus y squared if xy is not the origin, and 0 if xy is the origin. Now, we just figured out that this function was continuous at every value except the origin, right? You had, if you made a graph, you had a little hole there at the origin. This function's continuous at everything except the origin. So this guy, for any point other than 0, 0, it's continuous. The question is, did they plug it up so that at 0, 0, it's still continuous? In order to be continuous, the question is, it's a rational function. Rational functions define everything on its domain. Its domain was all reals but the origin. But since now they defined it, they gave it a definition at 0, 0. The question is, if I take the limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared, will I get f of 0, 0? And f of 0, 0 is 0. Because remember, you're continuous if the limit as you approach the point is equal to the value of the function at the point. So to figure out, am I continuous at 0, 0, I have to evaluate this limit. Well, I think to do that, what I'm going to do is, let's come in from the right. So I'm going to take the limit. How do I do a point on the right? I call it x0. So we're taking x0 approaching 0, 0. So notice when I take x0 approaching 0, 0, I'm letting x be x, but I'm letting y be identical 0. So if x is x, y is 0, x is x, y is 0, I'm getting a limit of 1. So coming in this way, I get a limit of 1. Wait a minute. Coming in this way, I get 1. The value of the function is 0. What does that tell me? Does the limit equal the value of the function? Coming in one pathway, if the limit was 0, that meant every pathway gave me of 0. I have one pathway with the limit equal to 1, which is not equal 0. Therefore, my function is not continuous at 0, 0. So this function is continuous at all reals except the point 0, 0. Okay? So for piecewise, you have to worry about, where you change the rules, does it match up? Let's try another one. How about this one? Now notice this particular function, at the whole number line except for 0, 0, all right? Everything out here, the function f of xy is equal to 3x squared y over x squared plus y squared. That's a rational function. A rational function is continuous on its domain. Its domain, the only thing I can make that to be 0 in the denominator is 0, 0. So I know this function, it's a given, this function is continuous at all xy except 0, 0. But now they defined the function to be 0 at 0, 0. So the question is, maybe this function, where they gave it a definition at 0, 0, might be continuous at 0, 0 also. So what we have to evaluate is, are we possibly continuous at 0, 0? You check continuity by taking the limit as xy approaches 0, 0 of f of xy and see, do I get f of 0, 0? What is f of 0, 0? F of 0, 0 is defined to be 0, right? Because if xy is 0, 0, they're defining the function to be 0. So if the limit as xy approaches 0, 0 equals 0, then we will be continuous at 0, 0. We already knew we were continuous every place else, so it would be at all of R2. Okay, so I have to evaluate the limit as xy approaches 0, 0. Now, as xy approaches 0, 0, it does not equal 0, 0, so this is the rule we use. This baby cakes cries out to me to use polars. Why? Because look what I got here. The numerator for x, I'm going to put in r cosine theta. For y, I'm going to put in r sine theta. And x squared plus y squared equals r squared. Well, my goodness, look here. The r squareds cancel. And I get the limit as r approaches 0 of 3r cosine squared theta sine theta. As r goes to 0, this is going to 0. This is going between -1 and 1. We're going to 0. So we just proved that the limit of this is always 0. And so therefore, the limit as xy approaches 0, 0 equals the value of the function. So we're also continuous at 0, 0. So this particular function, since it was a rational function, it was continuous at everything on its domain. But since they plugged it up at 0, 0, and in fact the limit was equal to the value of the function, this function is continuous on all of R2. And we all know what R2 means. It means all the two-dimensional vectors, right? This is all the points x, y, such that x is real and y is real. So in other words, it's the whole xy plane. Okay, let's do another one. This is easy. Determine the set of points at which this function is continuous. With rationals, rationals are continuous on their domain. What values get thrown out for the domain of a function? Those values that make the denominator 0. What would make 1 plus x squared plus y squared equal to 0? Nothing. You square x and y, you get 0 or bigger. You add 1, you're 1 or bigger. There's nothing there. So what's the domain of this function? Pardon? Don't tell me all reals, because your domain are points, ordered pairs, x, y. So it's not all reals, it's R2. Because you notice what you're doing is you're taking r cross r. Real number, comma, a real number. Piece of cake. Okay, composition theorem, this is from your Calc 1 days. It's the same thing. If f of x is continuous, but I'm going to call g of xy continuous, then f of g of xy is continuous. The composition of two continuous functions is continuous. So in this one, where is the function h of xy equal to arctangent of y over x continuous? Notice this function h of xy is the composition of two functions. First, you're taking the function f of xy, which is equal, and let's call that z. We're taking z, which is f of xy, which is y over x. And then we're taking the z, which is y over x, and we're taking the arctan of it. Okay? The arctan function, does anybody remember what the arctan function looked like? Remember what the graph of arctan looked like? Y equals arctan x. Does anybody remember what it looks like? It's a beautiful function. Its max is pi over 2. Its min is minus pi over 2. And the arctan function is a beautiful continuous function that looks something like that. Continuous is if you can draw it without lifting your pencil for single variables. Is that function continuous? Always. When is the function y over x continuous? As long, so this is a continuous function. Y over x is continuous as long as you can't have x equal to 0. So your domain is all reals except those points where x is equal to 0. If you wanted to draw it, what would that look like? X equals 0 is the y-axis, right? X equals 0 is the y-axis, and we're taking everything here and everything here, but the y-axis is out because x equals 0 is out. Not hard. Let's do another one. This function, what if I want to know for what values is this function positive? Not function, is this function positive? For what values is this function continuous? Well, people, exponentials are continuous. An x squared times y, that's a polynomial. It's continuous. E to the x, that's continuous. So this baby cakes is continuous for all reals. This one, x plus y squared, is always continuous. But there's a problem with the square root. With square root, what do you have to have? You have, well, zero's okay. Okay? You could say to Mrs. Strocko, it's okay for you just to write this. The domain is the set of all x, y, such that x plus y squared is greater than or equal to 0. You don't have to graph it. They just asked you to type the domain. Now, if you wanted to graph it, we're going to graph it, but they're not asking you to do that in your homework. Notice x greater than y squared is x is greater than or equal to minus y squared. You know what the graph x equals minus y squared looks like? Well, x equals positive y squared looks like this. But we're not doing x equals positive y squared. We're doing x equals minus y squared. So it would look like this. Okay? And notice if we want, let's try the point right here is 2 comma 0. If you plug in 2, 0, it works. So its domain is everything on this side. So this bizarre and peculiar function is only defined on this part of R2. For your homework, though, all they want is this. You don't even have to graph it. Okay? So this one, I chose this one because it's causing us to go back and remember the inverse trig functions. Inverse trig functions can act on what kind of numbers? You can only take the arc sine of what numbers? Can you take the arc sine of 2? Aha, you got to be between -1 and 1. So because you can only say, find me the angle whose sine is, right? Well, the sine of any angle is between -1 and 1. So we need to have x squared plus y squared to be between 1 and -1. We go, Mrs. Strocko, x squared plus y squared is always bigger than or equal to 0, so this -1 is not going to happen. This is as good as it gets. Right? So you could write this as the set of all x, y, such that x squared plus y squared is less than or equal to 1. 100% for the domain. Let's graph it, though. I mean, this one just cries out. I think in Calc 3 we should be getting a little bit better with our functions. Okay? What's x squared plus y squared equal 1 look like? It's a circle of radius 1. So where are all the points where x squared plus y squared is less than or equal to 1? The domain is only on that disk for that function. Everything out there, not defined. Pretty cool, huh? One more. This one. Oh, I'm lying. There's 2 more. Okay, this one. F of x, y, z. Uh-oh. The domain for this function's in R3, right? So my domain is going to be the set of all x, y, z such that what has to happen? X plus y plus z has to be greater than or equal to 0. Now what happens is this is a plane. X plus y plus z equals 0 is a plane. And going greater than or equal to 0, you're getting one side of that plane shaded in. All right, let's do one more. Ew. This one. We are asked to find on what values is this function continuous. Now notice this function is rational for all values except for, it's rational for all values except for x, y equal to 0, 0. How can I find out if I'm continuous at 0, 0? What do I have to do? Take the limit, huh? Now notice, a rational function is continuous on its domain. This rational function, 2x squared plus y squared over x squared plus y squared, if I just had z equals that, this function's continuous on the whole real number line except what value? 0, 0. That's right, because you'd have to put a 0 here and a 0 here to get 0. But now some smarty pants has come along and they said, well, let's define it at 0, 0 to be 1. So the question is, if I take the limit as x, y approaches 0, 0 of x squared y cubed over 2x squared plus y squared, will this equal f of 0, 0, which is 1? How do you want to do that? How do you want to do that? Polars are not going to cry out here. Polars are not going to cry out. And the reason is, if I had x squared plus y squared, that would be a quick r squared. The problem is I don't have an x squared plus y squared. I have a 2x squared plus y squared. Wouldn't it be lovely if the x squareds could cancel? Okay. I'm going to try the squeeze theorem. Now you guys are going to help me. We're going to try the squeeze theorem. I would like to get rid of that y squared. You with me? Because then the x squareds would cancel. So I say to myself, I'm not sure if this is going to work, but we're going to see if it does. 2x squared plus y squared is greater than or equal to 2x squared. Do we all agree with that? So if I take the reciprocal of it, and the reciprocal of this, how are they related? Less than or equal to. Sure, because if you have a fraction with a bigger denominator, it's going to be smaller. Now, I'm going to multiply by absolute value of x squared y cubed on both sides. This is less than or equal to that, right? Because this is positive. I made it absolute value. This is positive. What happens on this side? Goodbye x squareds. So as xy is going to 0, 0, this is going to 0. What's y cubed over 2 going to? 0. So therefore, the limit as xy goes to 0, 0 of absolute value of x squared y cubed over 2x squared plus y squared is equal to 0. Well, if the absolute value of something's going to 0, it's got to go to 0. And so therefore, my limit is equal to 0. But wait a minute. For this function to be continuous, we just figured out the limit was 0, but the value of the function was 1. So does the limit equal the value of the function? No. So this function is continuous on all of R2 except, if I can spell except right, the point 0, 0. You might want to write this as the set of all xy such that x does not equal 0 and y does. Or why don't we just say the set of all xy such that xy does not equal 0, 0. Okay? All right, I think we've done enough for today. What I would like you to do is read in your books, look over the examples. By the way, when you see the stuff in the examples with the epsilon delta proofs, skip that. All right? We're not doing epsilon deltas in here. All right? Other than that, and when they do a squeeze theorem, you try to do it with polars. Okay? And if polars work much quicker, use polars. And then I want you to do on pages 944 to 945, 1 to 19 the odds, and 27 to 37 the odds. Okay? It's been delightful. I'll see you next time. Thank you.